Hello and welcome to the third and last part of section 6.6, improper integrals. I'm going to go over the comparison theorem, and I'm not going to prove the theorem, but I'll draw some graphs to explain what's going on here, okay? Well, long story short, if we have that f and g are continuous functions, and we have that f of x is always greater than or equal to g of x, and they're both non-negative for x greater than or equal to a, then if the integral from a to infinity of f of x is convergent, then so is the integral from a to infinity of g of x. If the integral from a to infinity of g of x is divergent, then so is the integral from a to infinity of f of x. So let me show you what's going on here, and you'll see that it makes a lot of sense. So we see that f of x is always larger than g of x. So say we have something like this, say this is f of x, and then say that this is my g of x, and this is g of x. Who cares what they actually look like? But the important thing here is that f of x is greater than or equal to g of x, and then here we have a. Okay, so let's see if we can understand what this means. So in part A, we have that the integral from a to infinity of f of x is convergent. Now, what does that mean? It means that if I find the area in between, like from a to infinity, under the graph of f of x, then this area is finite. Well, g of x is always less than f of x. Therefore, the area under the curve g of x has to be finite, okay? Using the same idea, actually I can just move this. I'm just going to take this with me and put it here, right? Now, using the same idea, now for part, so this corresponds to part A. If we do the same for part B, and then again here we have the function, let me say again, f of x is still larger than g of x, and then we have g of x right here, right? And we still have a here, and then this corresponds to b. Then think of what part B says. Part B says that now if the integral from a to infinity of g of x is divergent, meaning if I compute the area under the curve of g of x, if it's divergent, then it means that it is not finite. Well, the fact that it's not finite tells me that if I then try to compute the area under the curve of f of x, it's not good. There's no way it could be finite, okay? So that's how, this is why this theorem works. Okay, beautiful. Let's do examples. So we have to use the comparison test to determine whether the integral is convergent or divergent. We have the integral from 1 to infinity of x plus 1 over root of x to the fourth minus x dx. Okay, so now the fact that we have some power functions here tells me that I should remind you of theorem number 2, okay? That theorem that tells you that if you have the integral from 1 to infinity of 1 over x to the p dx, and p is greater than 1, then the integral is convergent, and then if p is less than or equal to 1, then the integral is divergent, okay? So we want to be able to compare this integral to something that looks like 1 over x to the p. So let's see how we do this. So we're going from 1 to infinity, so we know that x is greater than 1, okay? So if this is the case, we have x plus 1 over root of x to the fourth minus x. So if instead of dividing by root of x to the fourth minus x, we divide by root of x to the fourth, then I'm dividing by something that it is larger, right? Therefore this is larger than x plus 1 over x to the fourth root of that, which is just equal to x plus 1 over x squared, okay? And then again, if my top is smaller, right? If we have x, this is larger than x over x squared, which is equal to 1 over x. And then, well, we know that since p is equal to 1 in this case, then we'll have that the integral diverges, okay? Why? Well, if we go back to the theorem, we see that f of x, which is our function, is larger than g of x, and g of x diverges, then, the integral from a to infinity of g of x diverges, then that's the case for f of x. In other words, let's go here. We say that, here we go, since x plus 1 over root of x to the fourth minus x is greater than or equal to 1 over x, and the integral from 1 to infinity of 1 over x dx diverges, then by the comparison theorem, the integral from 1 to infinity of x plus 1 over root of x to the fourth minus x dx also diverges, okay? Now we have to use the comparison test to determine whether the integral is convergent or divergent. We have to be careful here because we have the integral from 0 to infinity, and we're going to compare this integral to, well, the one from theorem 2, which is the integral from 1 to infinity of 1 over x to the p dx, okay? Not a problem. I can look at this and rewrite it as the integral from 0 to 1 of x over x cubed plus 1 dx, and then plus the integral from 1 to infinity of x over x cubed plus 1 dx. And then here, this first integral from 0 to 1, I mean, we can do this for using partial fraction decomposition. So we know that from 0 to 1, that's just a number. So I'm going to go ahead and say this is just a number, okay? So we have to take care of this integral right here. So let me write it. Let me take care of that function. So x is larger than 1, therefore x over x cubed plus 1. Well, we know that this will be less than x over x cubed, because here I'm dividing by something larger, okay? I have something larger in the denominator. Then I simplify this, I get that this is 1 over x squared, and this is all we need to apply the theorem, right? Well, I'm saying this because then now this is my f of x, okay? And this is my g of x. Well, not this one, but this one. This is my g of x, okay? So then I know that the integral from, so we say, well, since, let me just write the conclusion down. We say since 1 over x squared is larger than x over x cubed plus 1 for x larger than 1, and the integral from 1 to infinity of 1 over x squared dx converges, then by the comparison theorem, the integral from 1 to infinity of x over x cubed plus 1 dx converges, and the integral from 0 to infinity, right, of x over x cubed plus 1 dx converges, okay? Keep in mind that we didn't need to find the actual value of this integral. We just wanted to see whether it was convergent or not, okay? This is all I have for this whole section. I hope you enjoyed it. See you next time. Bye-bye.